So what does the microscopic silicon chip inside your smartphone have in common with the stomach of a dairy cow?
Oh man. On the surface.
Right, on the surface, absolutely nothing. I mean, one is this cutting-edge piece of human engineering, and the other is just, a biological fermentation vat.
Yeah, but if you actually strip away that surface, like if you look at the fundamental blueprint of the universe, they're the exact same machine.
They really are. And welcome to the deep dive, by the way. Today, we're pulling from this massive stack of sources. It's a comprehensive collection of junior high integrated science textbook summaries.
Yeah, we're talking a bit of everything. Biology, physics, chemistry, agriculture, electronics, all of it.
But, and I want to be clear here, our mission today is not to just sit here and read a textbook to you.
Yeah.
You don't need us to list out a bunch of facts you probably, memorized and forgot a decade ago.
No, definitely not. I mean, our goal today is to synthesize all these seemingly disconnected disciplines. We want to reveal a universal pattern.
Right. And that central theme, the hook that basically binds the entire universe together, is this concept of systems of inputs, processing, and
Yeah.
outputs. Because it doesn't matter if you're looking at a sprawling farm or a digital logic gate or literally your own beating heart.
Yeah.
Everything operates on that exact same structural loop.
Raw material goes in, a mechanism applies some rules to process it, and a transformed result comes out.
Exactly. So whether you're tuning in just to brush up on some core concepts or you're feeding that innate curiosity about how reality is built, this framework is going to change things for you.
Oh, for sure. By the time we're done, you're going to look at like the tools on your desk or the plants in your window or even the cells in your own body in a completely interconnected way.
So let's ground this. Let's start with the most intimate piece of machinery which is your own body.
Best place to start.
Specifically, the digestive system.
Yeah.
Because, well, a lot of people think chewing their food is just about making it small enough so they don't choke.
Right, right.
But the source has detailed this incredibly aggressive engineering strategy. The alimentary canal is essentially, it's an advanced chemical recycling plant.
I love that analogy. It really is a recycling plant because the ultimate goal of digestion isn't just making pieces smaller. It's taking massive, complex structures like a piece of bread and dismantling them into basic chemical building blocks.
Stuff your cells can actually absorb.
Exactly. And to do that, you have to optimize surface area.
Surface area. Okay, let's unpack this because the textbook lists the 4 types of teeth we have, right?
Right.
You've got incisors for cutting, canines for tearing, and then your premolars and molars for grinding. But the point isn't just the shape of the tooth.
No, it's not.
The mechanical processing is totally designed to expose as much surface area of the food as possible.
Because the chemical processors, the enzymes, they need physical contact to work. So while you're mechanically crushing a cracker with your molars, your saliva is actually flooding the input bay with an enzyme called amylase.
Right, and amylase targets starch.
Exactly. So the more you grind the cracker, the more exposed starch molecules there are for the amylase to latch on to. It starts dismantling them into simple sugars before you even swallow.
Wow. And then it drops down into the stomach, which is basically an industrial acid bath.
Pretty much, yeah.
You've got hydrochloric acid and pepsin, which goes to work on the proteins. But the real masterpiece of this surface area engineering happens in the small intestine, doesn't it?
Oh, absolutely. The small intestine is the ultimate sorting and absorption facility. It uses lipase to break down fats, but the architectural brilliance is in these structures called villi.
Villi, those are the microscopic finger-like things.
Right, exactly. Millions of tiny folding projections lining the wall of the intestine. Think about it. If the inside of your intestine was just a smooth tube, the food would slide right through.
Before anything could be absorbed.
Exactly. By covering the walls in these little fingers, your body exponentially increases the surface area for absorption into the bloodstream.
Okay, so we have this highly optimized chemical recycling plant. But wait, looking through the agriculture section, the sources mention that animals like cattle and goats have a 4-chambered stomach.
Ah, yeah, the ruminants.
Right. The rumen, the reticulum, the omasum, and the abomasum. Does that mean a cow is just a much more complex, heavy-duty version of our recycling plant? Like, is it just a superior machine?
I wouldn't say superior, it's just highly specialized for radically different input.
How so?
Well, you and I cannot digest cellulose. It's the tough, rigid fiber in plant cell walls. If you eat a bowl of grass, your recycling plant just can't extract the energy. It passes right through.
Oh, right.
But ruminants evolved to survive on that tough plant matter. So those four chambers are built out of necessity. They act as these massive fermentation vats housing symbiotic bacteria.
So the bacteria do the heavy lifting.
Exactly. They break down the cellulose. Our system just isn't equipped to process that kind of raw data, so to speak.
Which brings us to what happens when the system actually breaks down. Malnutrition.
Yes, system failure.
Because the textbook outlines malnutrition not just as, like, eating poorly. It's described as highly specific mechanical breakdowns based on precisely what input is missing.
Right.
I mean, if you over-input, the system strains under the weight, right? Obesity, cardiovascular failure. But undernutrition is fascinating because it shows you exactly what each raw material is building.
Think of it like an assembly line that runs out of a specific part. If your diet lacks protein, the output is kwashiorkor. If you're missing vitamin C, your body literally cannot synthesize collagen.
Which is the glue that holds your tissues together.
Exactly. And the output of that failure is scurvy, where your gums bleed and wounds won't heal.
Wow. And the textbook mentions rickets, too.
Right. That's a lack of vitamin D and calcium, so the bones literally soften and bend. Or if you lack iron, your bone marrow can't manufacture hemoglobin.
And without hemoglobin, your red blood cells can't transport oxygen, so you get anemia. Just profound systemic exhaustion.
Which is a terrifying output.
It really is.
Yeah.
And, every engine produces exhaust. To maintain balance, the body has to output metabolic waste. Like, the kidneys act as these strict filtration systems, pulling urea and salts to output urine.
Your lungs output carbon dioxide.
Right. The skin removes sweat. The liver intercepts toxins. If any of those output mechanisms jam, the biological engine basically poisons itself.
Which really forces us to zoom out, right? We have to look at the macro environment. Because an internal biological engine is strictly capped by the quality of the external inputs it receives.
Right. To keep the engine running, you have to guarantee the fuel supply.
And that's what agriculture actually is.
Exactly. We're scaling up from the micro, like the villi in your gut, to the macro management of the planet. Farming isn't just planting seeds. It's humans manipulating environmental inputs to maximize biological outputs.
And the medium for all of that processing is the soil. And just like the teeth in your mouth, soil efficiency comes down to its physical structure.
Right, the particle size.
Yeah. The sources categorize it. Sandy soil has large particles, clay has microscopic particles, and loamy soil is this balanced mixture of both.
I used to hear loamy soil described as the Goldilocks of dirt, but that never really helped me understand it. After reading these sources, I think a better analogy is brewing a pour-over coffee.
Okay, I like that. Let's follow that analogy.
So if your coffee grounds are too coarse like sandy soil, you pour the water in, and it rushes straight through to the bottom.
It drains way too fast.
Right, meaning the water doesn't have time to extract the oils or the flavor. In farming, sandy soil means the water leaves before the plant roots can process it, so they dry out and starve.
And if your coffee grounds are too fine, like an espresso grind packed down way too tight, that's your clay soil.
Exactly. It clogs, you pour the water in, and it just pools at the top, the water gets trapped. And here is where I actually want to push back on something in the text, because it seems a little counterintuitive.
Okay, what is it?
The sources talk about the immense effort we put into agricultural water management. We build these massive surface irrigation grids, elaborate sprinklers. We spend so much energy pumping water into the land.
Right.
But then the textbook emphasizes that we have to build equally elaborate drainage systems to pull the water right back out. Why pump it in just to drain it?
Well, if we connect this to the bigger picture, it's because of the biological limitations of the plant. Managing a macro system isn't just dumping raw inputs onto a processor.
Okay.
You're optimizing the environment so the biological machine can actually do its work. If clay soil traps the water, or if you over-irrigate without any drainage, you waterlog the soil.
But a plant drinks water. Why is waterlogging a death sentence?
Because plant roots don't just drink, they breathe.
Wait, really?
Yeah.
Right.
They require oxygen from the tiny air pockets in the soil to perform cellular respiration. If water fills all those air pockets, the root is plunged into an anaerobic state. It literally suffocates.
Wow. I had no idea.
Yeah, and without oxygen, the roots start producing toxic byproducts and they just rot. So Drainage is basically the critical exhaust pipe for your irrigation engine.
That makes perfect sense. It's about preventing toxic feedback loops. And the textbook actually expands on this with nutrient cycling,
Right, maintaining fertility.
because you can't just strip nutrients from the soil output after output. You have to put something back. So they use crop rotation, organic manure, or chemical NPK fertilizers, nitrogen, phosphorus, and potassium.
And the nitrogen cycle is a huge part of that. The sources mention legumes, which naturally harbor bacteria in their roots.
Right. They pull ambient nitrogen straight from the air and fix it right back into the earth. It's a natural closed-loop recycling program.
It really is. And the sources draw a direct line from that to general environmental health, emphasizing the 3 R's of waste management: reduce, reuse, recycle.
Because at a macro level, we have to make sure that toxic outputs of one system like human plastic waste don't become lethal inputs for the global ecosystem. So we've engineered the Earth to feed our biology. But humanity didn't stop there. We took this natural pursuit of efficiency and we codified it into the mathematical laws of physics.
And eventually into the digital architecture of our computers.
Yes, this is where we transition from biological wetware to mechanical hardware. Because in physics, the concept of processing is rigidly defined.
Very rigid. The definition of work is that it's only accomplished when a force actually moves an object a certain distance.
Work equals force times distance, measured in joules.
Right. So if you push a massive boulder with all your might for an hour, but it doesn't move a single inch.
Your biological engine did zero work, according to physics.
Exactly. Your input resulted in zero output. And power is simply the speed at which that work gets done, measured in watts.
But the textbook delivers a really harsh reality about physical systems here.
Yeah.
No mechanical machine is ever 100% efficient.
Never. The law of thermodynamics.
Whenever you process physical mass, the work output is always less than the work input. Some energy is inevitably lost to friction and heat. Gears grind, parts rub together, and energy just bleeds out.
Now hold on to that concept of friction and lost energy, because when we transition into ICT, information and communication technology, it takes on a really fascinating new dimension.
Right, because in the digital realm, we aren't processing physical mass with gears. We're processing invisible streams of data.
And the sources draw a huge distinction between data and information.
Yes, data is raw, unorganized facts and figures. It's the raw input of the universe, scattered, basically meaningless on its own.
Right. Information is what you get when a system processes and structures that data, so it actually means something to a user. Information is the useful output.
And the ultimate processors that turn that data into information are logic gates.
Yeah, these tiny electronic circuits inside your computer chip.
They make decisions based on binary inputs, 0 for off or low voltage, and 1 for on or high voltage. Here's where it gets really interesting. Let me throw an analogy at you for these gates, see if it holds up.
Okay, let's hear it.
So, the text highlights 3 primary gates: the AND gate, the OR gate, and the NOT gate.
Right.
The AND only produces a high output, a 1, if all inputs are high. So it's like having strict parents. Both mom and dad have to give you a yes before you can go to the party, 1 no, and the output is 0, denied.
That is perfect. It perfectly captures the strict contingency of an AND gate. Now contrast that with the OR gate, which acts like switches in parallel.
Right, the cool aunt or uncle. You ask 3 different relatives for permission, and you only need one of them to say yes to get your output.
Exactly. Just one high input gets you a high output. And then there's the NOT gate.
The inverter, right.
It only has a single input, and its entire job is to flip the signal. If you feed it a 1, it outputs a 0. If you feed it a 0, it outputs a 1.
It's the stubborn teenager of the digital world.
Yeah.
Whatever input you give it, it reflexively does the exact opposite.
I love that.
But, thinking about these clean mathematical gates brings up a conceptual question. We just said physical machines lose efficiency to friction. Do digital computers have a form of friction when they try to turn data into information? I mean, there's no gears grinding in a microchip.
This raises a really important question, and the answer lies in something called information entropy.
Okay.
Yes, digital systems face massive friction, but it's not mechanical heat. Digital friction is noise.
Noise.
It's the chaotic, unstructured degradation of a signal. If you just dump unstructured, noisy data into a system, you don't get information out, you just get digital chaos.
Oh, like a messy email inbox.
Yeah.
Or some unorganized spreadsheet.
Yeah.
That is raw data, and your brain has to spend excess energy, like literally burning calories, just to fight through the noise to find something useful.
Precisely. And in a computer, electrical signals physically degrade as they travel. A nice, crisp 5-volt signal representing a 1 might degrade to, say, 4.5 volts due to interference.
Oh, wow.
Yeah, and if the system doesn't correct that, the noise compounds until the data is totally destroyed. That's why digital logic relies on truth tables.
The charts that map every possible input to a strict output.
Exactly. Truth tables and logic gates aren't just calculators, they act like physical bouncers at the door of the system.
Bouncers.
Yeah, they enforce strict voltage thresholds. If a degraded 4.5-volt signal hits a gate, the gate recognizes it as a 1 and outputs a fresh, perfectly clean 5-volt signal on the other side.
It blocks the noise from progressing.
Yes. It's how humans engineered a way to build permanent order out of creeping chaos.
That is incredible. Okay, so we have mechanical systems processing physical force. We have digital systems using logic gates to fight chaos. But how do we as biological beings actually perceive all this structure?
Right, how do we interface with the universe?
Yeah, through the processing of light, which closes the loop nicely, bringing the physics right back to our biology.
The human eye.
Exactly. To understand how we input the visual world, we have to look at the physics of light. The text points out that the sun is a luminous source. It creates light. But the textbook on your desk is a non-luminous object. It just bounces the light.
Right.
But what I found fascinating was this rule of rectilinear propagation. The fact that light travels in rigidly straight lines.
Yeah, and that straight line travel is exactly why shadows exist.
Right.
When an opaque object blocks those straight rays, you get darkness. The darkest, sharpest core of that shadow is the umbra, and the softer, partial shadow around the edges is the penumbra.
But because light is so rigid, biology had to evolve a crazy complex mechanism to capture it.
And process it.
Exactly. Light bounces off the page straight into the eye. The cornea and the lens are specifically designed to refract or bend that rigid light.
To focus it.
Right, perfectly onto the retina, which is like the projection screen at the back of the eyeball. And from there, the optic nerve carries the electrical signal to the brain.
But just as a farm field can drown from waterlogging, or your body can break down from malnutrition,
The optical system can degrade.
highly prone to physical degradation, yeah.
So what does this all mean? Because this is where the synthesis really blew my mind. When the eyeball degrades, we literally use the physics of glass to artificially hack the biological input.
It's amazing. Let's look at the mechanics of that hack. Take myopia, or short-sightedness. You can't see distant objects. Why?
Because the lens is bending the light too sharply or the eyeball is too long.
Right. The light rays converge and hit their focal point before they reach the retina. By the time the light actually hits the screen at the back of your eye, the rays have crossed and they're spreading out again.
The input is just blurred noise.
Exactly. So, to fix a biological hardware failure, we place a concave or diverging glass lens right in front of the eye.
We force the light rays to spread out just a tiny bit before they even enter the biological lens.
Yes, which perfectly calibrates the focal point to land dead center on the retina.
That's brilliant. And conversely, with hypermetropia or long-sightedness, you struggle with near objects because the focal point is landing behind the retina.
So we use a convex converging lens to pre-bend the light inward.
The sources also detail astigmatism, where an irregularly shaped cornea scatters the light, and you need cylindrical lenses to fix it.
And presbyopia, right. The age-related stiffening of the lens, requiring bifocal.
It's the ultimate bridge between domains. The light bouncing off a non-luminous object in the room with you right now is just raw physical data. But the physics of refraction and the biological transmission via the optic nerve process that chaotic light into information.
Into an image your consciousness can actually comprehend. It proves the exact mission we set out to accomplish today. I mean, everything from a field of loamy soil, to a digital logic gate, to the rods and cones in your retina, operates on this unyielding cycle of inputs, processing, and outputs.
What a journey. I mean, we've moved from the chemical processing of enzymes dismantling proteins through the macro management of soil drainage into the strict math of binary computers fighting entropy, and finally to the way our own eyes hack physics to make sense of the universe.
Once you start viewing the world through the lens of systems, all those arbitrary boxes we put things in, they just disappear. You see how deeply interconnected the architecture of reality really is.
So here's our challenge to you for the rest of the day. Stop looking at the surface of things.
Yeah, look deeper.
Look at your coffee maker, your garden, your computer, or even the lunch you're about to eat. Identify the raw inputs. Look closely to find the hidden processing mechanisms at work. and actively measure the quality of the outputs.
You'll be amazed at the patterns you start recognizing everywhere.
And we want to leave you with one final provocative thought, drawing right from the physics textbook we covered. We established the inescapable law of thermodynamics. No machine is ever 100% efficient because the energy is always lost to friction and heat.
It's a hard limit on processing.
But if our brains and our bodies are also incredibly complex processors, taking in raw data, visual light, and food every single waking moment, what is the friction in your own daily mental processing?
That's a great question.
How much of your valuable limited daily energy is being lost to the heat of information overload? And most importantly, how can you adjust your own environmental inputs today to improve your system's efficiency? Usually when you look at an everyday object, let's say, the device you're using to listen to this right now, or even just like a glass of water sitting on your desk,
Yeah.
you really just see the surface.
Right.
You see the glowing screen, you see the clear liquid, and it feels, it feels completely simple, right?
Oh, absolutely. Because we rely so heavily on our macro perspective. We trust our eyes to tell us the whole story because, well, that's the scale we live on.
Yeah, but then you step into the world of integrated science, and suddenly you realize your eyes are essentially lying to you. Or at least they're kind of missing the main event.
Definitely missing the main event.
Because beneath that calm surface is this chaotic, highly structured, completely invisible machinery that is running absolutely everything in your life.
It is, yeah. It's the ultimate hidden rule book of the universe. I mean, the mechanics that govern a drop of water are the exact same mechanics that govern a star.
Which is wild. So, welcome to this customized deep dive. Today we're looking at a massive stack of notes you've shared with us, covering, well, basically the entire integrated science curriculum.
It's a lot of ground to cover.
It is. We are talking biology, chemistry, physics, earth science, agriculture. And our mission today isn't just to, memorize a syllabus or recite a textbook to you. We really want to connect the dots. We want to understand the why and the how of it all.
Exactly.
We want to see how an invisible, unimaginably small atom connects to the food on your table, the smartphone in your hand, and ultimately to the reality you experience every single day. So, okay, let's unpack this.
Well, to really understand that hidden rulebook, we basically have to start at the absolute bottom floor of reality. Before we can understand the world, we have to look at what it is actually made of. So we have to start with the atom.
Right. And I'm looking at your notes on atomic structure, and there's a phrase here that I actually need you to translate for me. It says the nucleus in the center contains protons, which are positive, and neutrons, which are neutral. Makes sense. But then it says they both have a relative mass of 1. Relative to what?
Ah, yeah, that is a great question. So atoms are so incredibly small that measuring them in standard grams or ounces is, well, it's mathematically exhausting.
I can imagine just tons of zeros.
Right, you'd be dealing with 20-something zeros after a decimal point. So scientists created a custom scale just for the subatomic world called atomic mass units.
Okay.
When we say a proton has a relative mass of 1, we mean it acts as the baseline yardstick for everything else. And a neutron is roughly the exact same size, so it also gets a 1.
So they're basically the heavy lifters sitting right there in the center of the atom.
Exactly. They contain almost all the weight. But orbiting around them, you have the electrons, which carry a negative charge.
And the notes say an electron has a negligible mass of about 1 over 1,840. That number is so specific, but my brain really struggles to picture that kind of scale.
It is tough. Think about it this way. If a proton is the size of a standard bowling ball sitting right in the middle of a massive football stadium.
Okay, bowling ball on the 50-yard line.
Right. The electron is a tiny grain of sand flying around the top rows of the bleachers at unimaginable speeds.
Right.
And that vast distance between the bowling ball and the grain of sand, that's entirely empty space. The device you are holding right now is mostly empty space.
That is just wild to think about. Okay, so if I'm thinking about these atoms like a giant box of Lego bricks, elements like pure gold or oxygen are your single-color bricks, right?
Yes.
Every atom in a bar of pure gold is identical. But then you have compounds like water, H2O, or table salt, NaCl. That's where it seems like the elements actually fuse together.
They form chemical bonds. You can't just mash them together. They combine in very specific fixed proportions based on how those tiny electrons interact.
It's like you have the instruction manual to build a very specific Lego spaceship,
Yeah.
and every single time it requires exactly 2 hydrogen bricks and 1 oxygen brick.
That's a perfect visual, honestly. And if you don't have those chemical bonds locking the pieces together, you just have a mixture.
A mixture being just like the jumbled pile of Legos sitting in the plastic bin.
Exactly.
They're occupying the same space,
Yeah.
but they haven't changed what they fundamentally are.
Which means you can physically separate them. I mean, if you mix salt and sand, no new substance is created. You could use a physical process like adding water, filtering out the sand, and then boiling the water away to get the salt back.
Oh, that makes sense.
Yeah.
And that leads right into the difference between physical and chemical changes. So, melting a block of ice is just a physical change. It's totally reversible.
Yeah.
The H2O molecules haven't broken their bonds. They just got warmer and started sliding past each other.
Right. But if you leave an iron nail out in the rain or throw a log on a campfire, that is a chemical change. It's totally irreversible.
Because the bonds break.
Yes. The iron reacted with the oxygen to create an entirely new substance, rust, with
But-
completely different properties. You can't just, cool down the smoke and ash to get your log back.
Right, right. But wait, if everything is just different arrangements of these Legos, how do we get completely different behaviors? Like shiny, bendable metals versus brittle non-metals.
What's fascinating here is that the arrangement of those outer electrons dictates almost the entirety of human technology.
Wait, really? How?
Well, metals, for instance, don't hold onto their outer electrons very tightly. They form what we call a sea of electrons that just drift freely between the atoms.
And that flowing movement is what allows metals to conduct electricity and heat so well.
You've got it. It also makes them malleable. When you hit a piece of metal with a hammer, the atoms just slide past each other in that fluid sea of electrons without breaking.
Okay.
Non-metals, on the other hand, hold onto their electrons with an iron grip. That makes them excellent insulators because nothing flows, but it also makes them brittle. If you hit a piece of sulfur with a hammer, it shatters.
But humans didn't just settle for what we dug out of the ground, right? We started playing with these chemical rules to create alloys, like bronze, which is copper, and tin.
Right. Human ingenuity is all about hacking the periodic table. Take plain iron. It is incredibly strong, but as we mentioned, it rusts easily, and it can actually be somewhat brittle under certain stresses. But if you melt it down and intentionally mix in a tiny, precise amount of carbon,
You create steel.
steel is vastly superior for building skyscrapers and suspension bridges. By slipping those smaller carbon atoms into the gaps between the iron atoms, it locks the whole structure into a rigid grid. We use the rules of chemistry to literally build the modern world.
That is amazing. Okay, so we've got these inanimate atoms, these alloys, and these compounds, but let's transition to how those very same elements power us. Because the human body is essentially a biological engine running on the chemistry we just unpacked.
It absolutely is.
Here's where it gets really interesting.
Sure.
Let's look at the air you are breathing right now.
To tie it back to our previous section, the air is a mixture. It's roughly 78% nitrogen, 21% oxygen, a tiny 0.03% carbon dioxide, and about 0.9% noble gases like argon.
See, I always get tripped up by that 78% nitrogen figure. If oxygen is the fuel we need to survive, why is the air mostly nitrogen? Does our body use it when we inhale?
We actually don't use the nitrogen we breathe in at all.
Really?
No, we exhale it right back out. But it plays a vital role as a planetary buffer.
Ugh.
Oxygen is highly reactive. I mean, it's the key ingredient in combustion. If our atmosphere was pure oxygen, a single lightning strike could cause a global firestorm.
Oh, wow.
Yeah, so nitrogen is incredibly stable, and it dilutes the oxygen to a safe, breathable level.
It's basically the packing peanuts of the atmosphere.
Yeah.
And what about those noble gases? Why do they get such a prestigious title?
It's a bit of chemical humor, actually. Remember how we said elements form bonds to become stable?
Yeah.
Noble gases like argon or helium are already perfectly stable. Their electron shells are completely full. Because they don't need anything from other elements, they refuse to interact or form compounds with the commoners, so to speak. They are chemically aloof.
I love that. Okay, so you take a breath to get that 21% oxygen. But how does the physical act of breathing actually pull that specific gas into our bloodstream?
It relies on a mechanical vacuum. You have a muscle sitting under your lungs called the diaphragm. When it flexes, it pulls downward, expanding your chest cavity.
So it's literally creating a vacuum.
Exactly. This lowers the air pressure inside your lungs, and the higher pressure air outside just rushes in to fill the void.
It travels down the trachea, splits into the branching tubes called bronchi, and finally ends up in millions of microscopic air sacs called alveoli.
The alveoli are the critical intersection of human anatomy. This is where the respiratory system shakes hands with the circulatory system. The walls of these sacs are incredibly thin, allowing the oxygen molecules to diffuse directly into the bloodstream, while the carbon dioxide waste diffuses out to be exhaled.
I like to compare the circulatory system to a massive, highly complex shipping logistics network.
Untack that analogy for me.
Well, think about the arteries. They carry the freshly oxygenated blood away from the heart. They are like the high...
For me.
Well, think about the arteries. They carry the freshly oxygenated blood away from the heart. They are like the high-speed, high-pressure, outbound highways of the body. The notes say they have thick, muscular walls.
They absolutely need those thick walls. Every time the left ventricle of your heart squeezes, it sends a violent shock wave of pressure through those arteries. If they were thin, they would burst immediately.
But the arteries eventually narrow down into capillaries, which the notes point out are only one single cell thick. Why do they get so microscopic?
Because that's where the actual delivery happens. The arteries are just the interstate. The capillaries are the tiny one-lane dirt driveways leading to literal door-to-door delivery. Because they are only one cell thick, the oxygen and nutrients in the liquid plasma can easily slip through the walls directly into your organ tissues.
And once the delivery is made and the garbage, like the carbon dioxide, is picked up, that deoxygenated blood has to travel back to the heart through the veins.
Right.
But here's my question. The pressure in the veins is much lower, and a lot of this blood has to travel all the way up from your feet. How does it fight gravity without just pooling in our ankles?
It's an elegant piece of biological engineering. Veins have tiny one-way valves built along the inside of the tubes. As you walk, your skeletal muscles naturally squeeze against the veins, pushing the blood upward.
Okay.
The moment gravity tries to pull the blood back down, those little valves snap shut. It's like climbing a ladder and having the rungs lock into place beneath you.
That is brilliant.
And it's crucial to understand why this entire logistics network matters. Your body is a machine performing continuous physical work. Your red blood cells carry the oxygen, the plasma carries nutrients, the white blood cells patrol the network as a security force looking for infections.
And the platelets.
They are the emergency maintenance crew, ready to clot and seal any leaks. It's all designed to keep the chemical reactions in your cells firing perfectly.
So we are basically these self-contained walking chemical reactors. But we don't exist in a vacuum. We have to interact with the world around us. Which brings us to ecology and agriculture.
We're moving from the microscopic inside our bodies to the macroscopic ecosystem. An ecosystem is simply the interaction between biotic factors, which are the living things like plants, animals, and bacteria, and abiotic factors.
Abiotic being the non-living things that dictate the rules of the environment, like the amount of sunlight, the type of soil, the temperature, the available water.
Correct. And energy constantly flows through this system. You have producers, which are your green plants, doing the hard work of turning sunlight into food via photosynthesis.
Right.
Then come the consumers, herbivores eating the plants, carnivores eating the herbivores. Finally, the decomposers, like fungi and bacteria, break down dead matter and return the raw chemical elements back to the soil.
It's the classic food web. And for plants to keep this cycle going, they have to reproduce. The notes detail pollination, how pollen transfers from the male anther to the female stigma. Sometimes they rely on abiotic wind to blow it over, or biotic insects to carry it.
And once fertilization happens, a seed forms. If that seed encounters the right abiotic conditions, sufficient water, oxygen, and a suitable temperature, it germinates and sprouts.
Which is great.
But this natural web is not always a peaceful place. It is full of invisible invaders looking for a free meal. Pathogens.
Things like bacteria, viruses, and fungi.
Yes. They cause infectious diseases, which spread from host to host, like tuberculosis or malaria. This is distinct from non-infectious diseases like diabetes or scurvy, which are internal system failures or nutritional deficiencies, not outside invaders.
The notes mentioned vectors, too, like how a mosquito transmits malaria or a housefly spreads cholera. They are essentially malevolent Uber drivers for these microscopic diseases.
That's exactly how they function, yeah. But humans don't just passively accept this battle. When I review the agriculture notes, it's clear that farming isn't just planting seeds.
No, farming is basically humans aggressively playing referee in a massive food web. We want our producers, the crops, to survive, and we want to completely eliminate any consumers that try to eat them before we harvest.
And we face massive threats. Agricultural pests like swarms of locusts or aphids that drain the sap from leaves, plus plant diseases like maize rust. To fight back, humans have developed sophisticated control methods.
Walk me through those methods. The notes list cultural, chemical, and biological control, along with water management like sprinkler versus drip irrigation and drainage to prevent root rot.
Let's start with cultural control. This is where we manipulate the farming practices to confuse or starve the pest. Crop rotation is a great example.
Okay, how does that work?
If a specific beetle loves eating your potatoes, and you plant potatoes in the exact same field year after year, you are just building an all-you-can-eat buffet for that beetle to multiply. But if you plant potatoes one year and then switch to beans the next, the beetle wakes up from the soil, finds no food, and dies off.
You're just pulling the rug out from under them. And biological control.
Biological control is intentionally bringing in a hitman. If aphids are destroying your crops, you don't necessarily need to spray poison. You can release thousands of ladybugs, which are natural predators of aphids. You use the biotic factors of the food web to do the dirty work for you.
That's so smart. And chemical control is obviously using pesticides and fungicides to just eradicate the threat directly.
Right. And if we connect this to the bigger picture, there is a powerful parallel here between agricultural control and human medicine. Think about immunization.
Oh, like vaccines.
Exactly. When we give a human a vaccine, we are proactively teaching their white blood cells to recognize the specific shape of a viral pathogen before it attacks. Both crop protection and vaccines are strategic preemptive defenses. We are using our deep understanding of biology to protect our systems from microscopic and macroscopic invaders.
We're constantly securing the perimeter, whether it's the bloodstream inside our bodies or a field of maize outside. Okay, we've seen how humans manipulate biology and chemistry. Let's pivot to how we manipulate the raw, unseen forces of physics to build our modern technological world.
This brings us to work, energy, and power. And in physics, work is a very strictly defined concept. It isn't just sitting at a desk thinking hard.
Right, the formula is work equals force multiplied by distance.
Meaning, if you push against a solid brick wall with all your might for 10 hours, you might sweat and exhaust yourself. But because the wall didn't move a single inch, from a physics standpoint, zero work was done.
But if you push a shopping cart 10 feet, work has occurred.
Exactly. And that work is measured in joules.
But then the notes introduce power. How does power differ from work?
Power is simply the speed at which you get that work done. It's work divided by time, measured in watts. If you carry a heavy box up a flight of stairs in 10 minutes, or run that same box up the stairs in 10 seconds, the total amount of work is identical because the force and distance are the same.
But running it up takes vastly more power.
Precisely.
To make all this work easier, humans invented machines, which provide a mechanical advantage. Pulleys, levers, gears. But the notes highlight a harsh reality. No machine is ever 100% efficient.
Because of friction. Whenever moving parts rub against each other or even push through the air, some of your input energy is stolen and converted into heat.
Let's talk about heat, actually, because the notes list 3 ways heat transfers: conduction, convection, and radiation. What is mechanically happening at the atomic level in each of these?
Let's visualize the atoms again. Conduction happens mostly in solids. Imagine a crowded mosh pit at a concert. If you heat up one end of a metal spoon, the atoms there start vibrating violently. They bump into their neighbors, who start vibrating and bump into their neighbors, passing the kinetic energy down the line until the handle burns your hand.
Got it. And convection.
Convection happens in liquids and gases. When you heat up air, the atoms spread out. Because it's less dense than the cooler air around it, the hot air literally rises, like a hot air balloon, carrying the heat with it. Cooler air rushes in below to fill the space, gets heated, and rises too. It creates a continuous flowing current.
But radiation is totally different, right? Because the sun's heat reaches Earth through the vacuum of space where there are no atoms to vibrate or rise.
Exactly. Radiation is the transfer of pure energy through electromagnetic waves. It doesn't need a medium, it doesn't need atoms, it just shoots across the void.
Which perfectly transitions into electromagnetism. I know magnets stick to my fridge, and the notes say opposite poles attract, well, like poles repel. But why is electromagnetism considered one of the biggest game changers in human history?
Because permanent magnets, like the ones on your fridge, are weak and you can't turn them off. But scientists discovered that flowing electrons, an electrical current moving through a wire, naturally generate a weak magnetic field around them.
So if you take a wire, wrap it tightly into a coil around a soft iron core, and flip a switch to send electricity through it.
The magnetic field from the wire aligns all the atoms in the iron core, creating an incredibly powerful magnet. And the best part, The second you turn off the electricity, the magnetism vanishes.
That's crazy.
We suddenly had the power to control immense magnetic forces on demand. This is the foundation of electric motors, generators, and the entire power grid.
Okay, I get that electricity flows in a closed circuit, and we can wire it in a series with one path or parallel with multiple paths. I understand how it spins a motor. But I have to admit, I struggle with the leap from raw electricity moving through a copper wire to a computer actually thinking. I get that electricity flows in a closed circuit, but how exactly does a simple electrical flow suddenly make decisions inside a computer?
It's all about logic gates. This is the foundational architecture of the digital world. A logic gate is a microscopic physical switch on a microchip. It receives electrical inputs and decides whether to send an electrical output based on one specific, rigid rule.
Like a 1 or a 0.
Right. In digital logic, we call a high voltage flow a 1 and a low or 0 voltage flow a 0.
Okay, 1 is electricity flowing, 0 is no electricity flowing.
Let's look at the A and D gate. Imagine a bank vault that requires 2 people to open it. The manager has a physical key. 80, the teller has a passcode. If only the manager turns the key, the door stays shut. If only the teller enters the code, the door stays shut.
The vault only opens if input A and input B happen simultaneously.
Yes, and A and D works exactly the same way. It only spits out a 1 if both of its input wires are receiving a 1.
Both conditions must be met.
Yeah.
And the OR gate.
Think of the automatic sliding doors at a grocery store. The door will slide open if the motion sensor inside detects someone or if the sensor outside detects someone. As long as at least one sensor sends a signal, a 1, the door opens.
And a not D gate.
The NOT gate is simply an inverter. Whatever goes in, the exact opposite comes out. If the input is a 1, the output is a 0. If the input is 0, the output is 1.
The notes mention mapping these out on something called a truth table. What is that?
A truth table is just a simple grid that maps out all the possible inputs a gate could receive and shows you exactly what the output will be. It's basically a cheat sheet for the logic.
But again, it's just 1s and 0s. It's bank vaults and sliding doors. How does that make a computer capable of generating the graphics on my screen?
Well, this raises an important question about scale. A single A and D gate is incredibly dumb. But when human engineers layer billions of these microscopic gates together in impossibly complex, cascading patterns, the output of one gate triggers the inputs of a dozen others.
Oh, wow.
Suddenly, those basic rules can process complex mathematics, render high-definition video, and connect you to a global internet. The magical digital reality you interact with every day is quite literally just the physical flow of electrons being mathematically corralled by billions of tiny logical rules.
That is genuinely mind-bending.
It's the ultimate application of integrated science.
So, for our final zoom out, we have to leave the human scale entirely. We've gone from the atom to the human body, to the farm, to the computer chip. Now let's look at the planetary scale, the ultimate closed system that houses everything we've just discussed.
Our solar system, the sun sitting at the center, providing that radiant heat we talked about, and the 8 planets locked in orbit.
And the physical movement of our specific planet dictates the rhythm of all biology on it. We have rotation, the Earth spinning like a top on its axis every 24 hours, giving us our day and night cycle.
Okay.
And we have revolution, our 365.25-day orbit around the sun.
And because the Earth's axis is slightly tilted, different hemispheres get more direct sunlight at different points in that revolution, which drives our seasons. Even the moon plays a role. Its gravity pulls on our oceans as it orbits, creating the tides.
Yeah.
But perhaps the most vital physical feature protecting this entire system is the atmosphere.
Right. The air we talked about breathing earlier, it sits in layers. We live in the troposphere, which is the lowest layer where all our clouds and weather happen. Above that is the stratosphere, which houses the ozone layer, acting like planetary sunscreen to block harmful ultraviolet radiation.
But here is where the integrated curriculum brings a stark warning. We talked about how human ingenuity hacks chemistry and biology to build our world. We forge steel, we use pesticides, we burn fuels for power. But there is a massive cost, and it's called pollution. We see soil pollution from pesticides and non-biodegradable plastics, and water pollution from oil spills and sewage.
So what does this all mean? The notes talk about acid rain and ozone depletion, but how do those mechanisms actually work?
It's just more chemistry, but this time it's working against us. When we bring fossil fuels in factories, we release sulfur dioxide gas into the troposphere. It drifts up, chemically bonds with water vapor in the clouds, and creates sulfuric acid.
Which is bad.
Very bad. It rains down, destroying forests and turning lakes toxic. Similarly, synthetic chemicals called CFCs, which we used in old refrigerators, drift up into the stratosphere and literally rip apart the chemical bonds of the ozone molecules, destroying our UV shield. And prevention, like reforestation and waste management, is a massive uphill battle.
It really highlights how fragile this spaceship we are traveling on is. Despite mastering steel alloys and building complex biological irrigation and wiring logic gates, we are still entirely dependent on a shockingly thin layer of troposphere. If we mess up the chemistry of that thin layer, the whole biological engine stalls.
That is the ultimate synthesis of all these notes. The laws of physics and chemistry, from the invisible atoms to the logic gates, are completely unbending. You can't break the law of conservation of energy. Matter just changes form. But biological and ecological health? That is terrifyingly fragile. A food web can collapse. The tiny alveoli in your lungs can get permanently damaged by air pollution. Root zones in agriculture will drown if the abiotic drainage fails. How we manage the balance between our relentless technological advancements and our fragile environment is the ultimate test of integrated science.
You really can't isolate the chemistry from the ecology. Well, I want to thank you for joining us on this massive scale-jumping expedition today.
It is a pleasure.
We started at the absolute bottom floor with an electron flying around an atom's nucleus. We traveled up through the high-pressure muscular arteries of the human heart, out into the complex food webs and predator-prey dynamics of a farm, zoomed through the microscopic logic gates of a digital microchip, and finally flew out into the massive orbit of the Earth around the sun.
It's a profound way to view the everyday reality around you.
It really is. And I want to leave you with one final thought to mull over based on everything we've covered today. Since atoms undergo chemical changes but are never fundamentally destroyed, every single atom of oxygen you breathe in right now, and every single atom of carbon locking together to build your cells today, is billions of years old.
They are the ultimate recycled material.
Exactly. They might have once been part of an ancient fern, the blood of a dinosaur, or an exploding star. The question is, a million years from now, what will your atoms be a part of next?
Keep questioning the invisible rules around you.
Thanks for joining us. We'll catch you on the next Deep Dive. Imagine you spend, like, 8 straight hours pushing against a solid brick wall.
Yeah.
You are sweating, your muscles are burning, you are absolutely exhausted. But according to the strict laws of physics, you haven't done a single drop of work.
It sounds like an insult, honestly, but mathematically it is the absolute truth.
And that is exactly where we're starting today. Welcome to the Deep Dive. We are looking at a huge mountain of information today, specifically a comprehensive digital archive of an integrated science syllabus.
Right, and if you were to just glance at this, it looks like 4 totally disconnected subjects. You've got physics formulas, digital electronics, human biology, and agricultural science.
Yeah, but we aren't here to just read a textbook to you.
Oh, far from it. Because when you strip away the distinct vocabulary of those different fields, you find one unified rulebook. We are looking at the universal systems of flow, work, and control.
Exactly. By the time we're done here, you're going to see how a playground, seesaw, the smartphone in your pocket, and, a massive field of wheat are all running on the exact same hidden logic.
It's all connected.
Okay, let's unpack this. Let's go back to that brick wall. Why am I doing 0 work? I mean, my arms are basically falling off in this scenario.
Because your muscles are expending energy, sure, but you aren't actually transferring that energy to the wall in a way that moves it. In physics, work, which is measured in joules, by the way, has a very specific definition. It is force multiplied by distance.
Gotcha.
So force you apply must cause an object to move in the direction of that force. No distance moved, no work done.
Okay, so to actually do work, I need to move a physical load.
Right.
But as humans, our physical capacity to push or pull things is pretty limited. Like, I can't lift a boulder with my bare hands.
Right.
So we invented simple machines, levers, pulleys, inclined planes. But here's what always trips me up. If I use a lever to lift a boulder I couldn't normally lift, isn't that essentially creating free energy? I'm getting out way more force than I'm putting in.
If we connect this to the bigger picture, that is the ultimate illusion of simple machines. It feels like magic, but the universe never gives you something for nothing. What you are experiencing is mechanical advantage. The machine is multiplying your force. But the trade-off is distance.
Ah, so there is a catch.
Always a catch. Let's look at the lever, like a long crowbar. To lift a heavy rock on one end by just, say, 1 single inch, You might have to push your end of the crowbar down by 2 or 3 feet.
Right, right.
You are trading distance to get that multiplication of force. Physicists call that trade-off the velocity ratio.
It's basically an exchange rate. I pay in distance, I get back force. But the syllabus points out that this exchange rate is never a perfect one-to-one, right?
Never. And that brings us to efficiency. In a perfect world, the work you put into a machine would perfectly equal the work you get out. But in reality, efficiency is always less than 100%. The universe charges a tax on every movement, and that tax is friction.
The friction tax.
Exactly. When metal scrapes on metal in a pulley or a rope bends, you lose some of your input energy. It literally bleeds off into the surrounding environment as heat.
Which is just wasted energy.
Yeah, basically. Heat is simply energy flowing from a hotter object to a colder one. The archive details the 3 ways the universe steals this energy. There is conduction, where heat travels through solid objects, like a metal spoon getting hot when left in your tea.
Okay, yeah.
There is convection, where heat moves through fluids or gases, like boiling water circulating in a pot. And then radiation, where heat travels as electromagnetic waves, which is, how the sun's energy reaches Earth through the vacuum of space.
And temperature, measured in Celsius or Kelvin, is just our human way of measuring how intense that energy transfer is at any given moment.
Precisely.
So we build these mechanical machines, we accept the friction tax, and we trade distance for force. But obviously, humanity didn't stop at physical levers. We got tired of paying that heavy friction tax on physical moving parts, so we figured out how to move something invisible instead, electrons.
The jump from mechanical systems to electrical ones is profound. We stopped moving water or heavy rocks, and we started managing the flow of electrons through conductive materials like copper.
And what blew my mind in the archive is how this flow intersects with magnetism. I always thought of magnets as just, rocks you stick to your fridge. They have a north and a south pole, opposites attract, like poles repel.
The basics.
But the syllabus dives into electromagnets.
Uh-huh.
Can you walk through how that works? Can we literally just turn a magnetic field on and off with a light switch?
We can. And what's fascinating here is that specific ability is the bedrock of modern technology. If you take a coil of wire, wrap it around a soft iron core, and run an electric current through that wire, you generate a magnetic field.
Wow.
Because electric current is just the flow of electrons, when you stop the flow, the magnetic field instantly vanishes. You're controlling fundamental forces of nature on demand.
But to control that flow, you have to build a track for it, a circuit. You need a source, like a cell or battery, to push the electrons, copper wire to carry them, a switch to control them, and like a light bulb to actually consume the energy.
And you have to be very careful about how you design that track. The sources break down 2 main types of circuits, series and parallel. Think of a series circuit as a single, continuous loop.
Like a one-lane highway. Every single electron has to travel through every single component in order, which means if one thing breaks,
the entire system goes dark, the physical path is broken. That's why engineers develop parallel circuits. Instead of a single loop, the circuit branches out into multiple separate paths.
So if one branch gets cut, the electrons just divert and flow down the other branches.
Yeah.
The system survives.
Exactly. It builds redundancy into the flow. They operate completely independently.
So we have these branching paths, and we can turn flow on and off. But how do we get from a simple light switch to a computer that can actually calculate and make decisions?
Yeah.
The archive spends a lot of time on logic gates, and I'm going to really dig into this because it feels like the missing link between electricity and artificial intelligence.
It absolutely is the missing link. A logic gate is basically an electronic intersection that receives incoming signals, electrical currents, and makes a strict decision about what to send out the other side. In the digital world, we represent this as binary. A high voltage is a 1, a low voltage is a 0.
Okay, so let's look at the A&D gate.
The A&D gate is, it's like the strictest bouncer at the club. It has 2 inputs. It will only output a 1, meaning it only lets the current flow through if input A and input B are both 1. If either is 0, the output is 0.
And you have the OR gate, which is way more relaxed. If input A is 1 or input B is 1 or both, it outputs a 1.
Sure.
It just needs something to work with.
Right. And then there's the most interesting one, physically, the Nazi gate, or the inverter. It only has 1 input. If a 1 goes in, a 0 comes out. If a 0 goes in, a 1 comes out.
I joked when I read this that the not T gate is just the digital equivalent of that contrarian friend we all have. You say yes, they automatically say no.
That's a great way to put it.
But how does a physical wire actually invert a signal? Is it magic?
It's not magic. It's incredibly clever plumbing. Imagine a pipe with water flowing through it. That's your 1. The NOT gate contains a physical switch inside it. When that incoming voltage that one hits the gate, it activates a switch that literally diverts the main power source straight into the ground. It drains the pipe.
Oh,
So
wow.
the output side gets absolutely nothing, a zero. Conversely, if no voltage hits the switch as zero, the main power is allowed to flow straight through to the output, creating a 1.
That is brilliant. It uses the input to block the flow.
And engineers use what are called truth tables to map out every single possible combination of inputs and outputs for these gates.
So you take millions of these gates, chain them together into massive parallel circuits, and suddenly you have a maze where electrons are forced to navigate these truth tables at the speed of light.
Which is exactly what the processor in your laptop is doing right now. It is just billions of tiny electronic gates opening and closing, routing flow based on strict physical logic.
It makes human engineering look like the absolute pinnacle of design. But here's where it gets really interesting. As I was reading the biology section of the archive right after the electronics section, it hit me. We are so proud of our parallel circuits and our logic gates, but nature engineered a vastly more complex, self-repairing circuit billions of years ago. And you and I are sitting here relying on it to stay alive.
The human cardiovascular system, it is the ultimate biological transport network.
And the parallels to the electronic circuits we just talked about are uncanny. Instead of a battery pushing electrons, nature uses a muscular pump, the heart. But the archive breaks the heart down into 4 distinct chambers. 2 atria on top, 2 ventricles on the bottom.
Oh.
Why 4? I mean, a basic water pump usually just has an in pipe and an out pipe.
Because the body is actually running